Okay, so let's pick this up here. If we want to integrate 2 sine x minus 5e to the x, well, let's just take a look at each one of these individually. We could do them individually. So integrating 2 sine x, I have a multiplicative 2. Then I want to integrate sine x. Well, that would come from cosine x, but the problem is cosine gives negative sign on derivative, so I need a negative to make up for that. So that gives me negative 2 cosine x. Then minus, I have a multiplicative 5, and then I want to integrate e to the x. But e to the x just comes from itself, so I get e to the x, and I have a plus c, and it's done. All right, integrating tan squared y plus 1. So you might think that I should just do integral of tan squared y dy plus integral of 1 dy. Because, well, integral 1 dy looks nice, but the problem is I don't know how to integrate tan squared y. I don't know a function whose derivative is tan squared. So this is not incorrect to do, but is not going to lead me anywhere that I would want. Instead, I should notice that, oh, tan squared y plus 1. I actually have a trig identity that says secant squared y is tan squared y plus 1. That doesn't immediately mean it's the right thing to do, but let's take a look. That would mean that this is actually integral secant squared y dy. Now, why is that better than what we started with? Well, because we actually know something that has a derivative secant squared, and that's tan. So I would get tan y plus c, and that's the answer. Okay, let's do another one of these differential equation problems where basically we're starting with derivatives and going to the original function. So again, we're starting with a second derivative, but we're also given some values that are going to help us. So to get the first derivative, I would integrate the second derivative. That would mean integrating x to the minus 3/2 dx. Okay, that doesn't seem too bad. It's just the power. So that gives me x, add 1 to the negative 3/2 gives me negative 1/2. Divide by negative 1/2 is the same thing as multiplying by negative 2. All right, and then I get a c. The other way I might want to look at this is negative 2 over the square root of x plus c. That might make it easier when I do evaluations, because the next thing I want to do is I want to figure out what that plus c is. Well, that's where I go back here and I use the fact that I know f prime of 4 is 2. But that's also what I would get from putting in 4 into this function. So negative 2 over the square root of 4 plus c means 2 is, so negative 2 over square root of 4 is negative 2 over 2, so negative 1 plus c. And that means if I add the 1 over, I get that c here is 3. Meaning that my first derivative with the plus c filled in is negative 2 over the square root of x plus 3. Now, in order to proceed, I might want that in a different form. I want that back as negative 2x to the minus 1/2 plus 3, because now that I'm going to go and do another integration, so to get the actual original function, I would integrate the first derivative, which now I'll use the one that has a power, negative 2x to the negative 1/2 plus 3. All right, dx, don't forget your dx there. And doing that, I have a negative 2 constant. I integrate x to the negative 1/2. So I add 1 to negative 1/2, giving me x to the 1/2, and divide by 1/2, which is the same thing as multiplying by 2. So this 2 becomes a 4. So I get negative 4x to the 1/2. Then plus 3x, because that's how I would integrate 3, and then I get another constant, which here I'll call d. Now the idea is I need to find d. I'm going to use f of 0 equals 0. So f of 0 equals 0, but that also means that's what I get when I plug 0 in here. So negative 4 times 0 to the 1/2 plus 3 times 0 plus d. Well, these are both 0, so that means that just d is 0. So finally, I can fill out my function. F of x is negative 4. Now, instead of x to the 1/2, I might just write square root of x plus 3x, and then d is 0, so it doesn't come there. So there is my answer. And what I've done was I solved the differential equation, which in this case meant going from a second derivative back to the original function, being able to fill in those constants that came up because I had some values to use.